This section is called the photoelectric effect. And what we're looking at when we look at the photoelectric effect is we're looking at how does light function? Light as in what we see. So in grade 10, you would have done light waves, which are transverse waves, and sound waves, and then you would have done a section called the electromagnetic spectrum. And in the electromagnetic spectrum, you would have come across things like radio waves, infrared, visible light, X-rays, ultraviolet lights, and so on. But what we do in grade 12 is we look at how this light actually functions. The Earth's atmosphere gives us the color of the sky. It gives rise to very surprising light phenomena such as mirages or rainbows. And some phenomena are so familiar to us that we often take them for granted. For example, why is the sky so blue on a clear day? Or why are sunsets red, orange, purple? Why is the night sky black? All these questions may seem naive, but their answers are not as simple and involve a physical phenomena that we will try to clarify in this section. So the first thing we need to look at is we need to understand what is light. So in some ways you've looked at light when you looked at the electromagnetic spectrum. And what we're going to do is, if I had to look at light, this is what light actually looks like. I've got here a Cartesian plane that's in 3 dimensions. If I look at the one transverse wave, you can see me highlighting it. Notice about this transverse wave, it's perpendicular to the axis, right? Up and down. And you understand this from grade 10, we introduce you guys to transverse waves. So we can understand a crest, a trough, and so on. Now light waves, this is what light waves actually look like. Right? You've got the one that's perpendicular to the surface, and then you've got the other wave that is perpendicular to that transverse wave. So you've basically got 2 transverse waves which are perpendicular to each other, and they sit on an axis. Now the one transverse wave is generating an electric field, and the other transverse wave is giving out a magnetic field. So what we can say is, we can say that light is a superposition of electromagnetic waves. So such a wave, a light wave, includes both an electric field, which we represent by using a capital letter E, or a magnetic field. And we'll use the letter B to represent magnetic fields. And these 2 fields, we can say, are oscillating at the same frequency. Now, some of these words you haven't seen in grade 11 because we don't address them in grade 11s. We look at them now in grade 12. So words like frequency, period, lambda, all of those words are going to come through. So these 2 fields, the 2 fields are perpendicular to each other. They're perpendicular to each other. And they keep moving together. So you've got this propagation of electromagnetic waves, and it's carried out at a certain speed. So with light, the speed of light is a constant, which we'll find on our formula sheet. And the letter we use for it is C. That's our symbol. And it's at 3 times 10 to the power of 8 meters per second. That is the speed of light. Right, so that's the first little bit. Right, the second bit is a little bit about light. So light is a transverse wave. It can travel through a vacuum. What that means is a vacuum is a space that has no matter or even no atoms. And a good example of vacuum is outer space, right? They do not require any medium. What that means, a medium is, we have different types of mediums. We have solids, liquids, and gases. So for example, with solids, we could be talking about a concrete wall, metal, whatever the case is. Liquids is any type of water bodies, and gases is just normally air. Light doesn't need a medium, it can just go, right? It does transfer energy from one place to another. They travel at the same speed, which we spoke about now, which was 3 times 10 to the power of 8 meters per second. And they obey the wave speed equation, right? Wave speed equation is a velocity. I'm just going to write this next to it. V is velocity in meters per second. So I'm just going to write this down here now so that we don't forget in the future. F stands for frequency in hertz. You would have done this in grade 10. I'm just going through it now. And lambda stands for wavelength. And we measure that in meters. When an electromagnetic wave travels from one medium to another, its speed and its wavelength change. Frequency does not. That just means that I'm going to get things like reflection. I can get stuff like refraction. Refraction, right? They obey the laws of reflection and refraction. There is no electric charge. They comprise of electric and magnetic fields that are at 90 degrees, that oscillate at 90 degrees to each other. So please make sure you taking down these notes, you putting them into your books. It's very, very important. I'm not only doing the revision from grade 10 to get you up to speed and just jog your memory. I'm also looking at the stuff that we're going to be using this year. So all these notes, little notes, equations, diagrams, drawings, graphs, they need to be in your books. The whole point of this video is to make sure that you're engaging with the topic. You need to take initiative. I should see plenty of notes in your books when you're done with this section, with these videos especially. Right, now, you remember this probably from grade 10. And in grade 10, they do it very quickly, but in grade 12 here, this is where we have a big focus on this section. So what we're looking at here is the electromagnetic spectrum. Now, the electromagnetic spectrum has, it starts off here with radio waves, and I want you to just have a look here. On the left-hand side, we've got radio waves, and they have very long wavelengths. Right? On the other end, you've got gamma rays, and what you've got there is a short wavelength. Right? Their frequencies work a little bit differently. If I have a long wavelength, then I've got a low frequency. If I have a short wavelength, I have a high frequency. Now, this is important to us because of the types of dangers that we look at. So if I have a low frequency, then I have a not so dangerous light wave. As in radio waves, microwaves, they can't harm you that much. But if I have a high frequency, it has a high penetrating ability. Now what that means is it can go through and through you. So if gamma rays hit you, it will go through your body. Right? X-rays, they go through the soft tissue to the bone and then they reflect back. Gamma rays go through and through. So you think of things like the Hulk, right? That's what the Hulk was exposed to, high frequency. This is where we see danger. And you see, you've got ultraviolet lights, that's UV from the sun that can create skin cancer and so on if you have too much of exposure. So you're going from not so dangerous on the left hand side to very dangerous on the right hand side. Now the only kind of light that we can see with our naked eye are colors. And the colors that we use are the colors in the rainbow. So we go from red all the way to violet. So when we have, what you must understand is when we have red light here, we have long wavelengths and low frequency. When we go to the end here and we have violet, we've got short wavelengths and high frequency. So the two types of lights that we're going to focus on in this section when we do towards the end of the section is red light, which is closer to the left hand side of the spectrum, and violet light or blue light, which is more towards the right hand side of the spectrum. So know the spectrum, understand the spectrum, understand the difference between wavelength and high frequency, low frequency, and so on. So the first thing that we must get into is the idea of the photoelectric effect. So the photoelectric effect cannot be explained if we only consider light to be a wave. So light has dual properties. So that means light is, firstly, it's a wave, and we've seen the wave. But light is also a particle. And we're going to get into that now. So Einstein explained that the photoelectric effect by considering light to have this particle nature. Now, we know properties of waves. We looked at it in the previous little bit. But now we have to look at the difference between a wave and a particle. So when we look at properties of waves and particles, we know that waves have frequency, wavelength, and amplitude. But the particle side of light, right, that gives you mass, it has size, it has kinetic energy, it has momentum. So when we're looking at light in this section, our main focus is going to be on the electrons. So we're going to look at electrons in the outermost shell. And we look at this in grade shell or energy level. And you look at this when you're in grade 10, when you're learning about electrons and so on, and about Bohr diagrams. You look at valence electrons. So what we're going to look at is we're going to look at electrons in the outermost shell or energy level of metals. That's our main focus here. So we're looking at those valence electrons. So what happens in this little section is we have a light that is incident. Incident means it shines on a metal. And what's going to happen is the valence electrons will escape from the surface of the metal. All right. Now, in order to escape, they must be given enough energy. Think about it like this. In order for you to come to school and have a productive day, you need to eat enough food. You need to have enough food in your system in order for you to carry out your school day. This situation works in the exact same way. We're going to shine a light onto a piece of metal, and the electrons are going to jump off. But those electrons must have enough energy. If they don't have enough energy, then you're going to have a situation where they're not jumping off. So what we want to achieve essentially is we want some kind of light to come through onto a piece of metal. It can be a red light, or we're going to use mostly red and blue lights. And it's going to come in, and when it comes in, it's going to knock these electrons off the metal. Please make sure that this diagram is in your books. So what we're looking at then is we're looking at something called the photoelectric emission. The photoelectric emission is the release of electrons from the surface of a metal when electromagnetic radiation in other words light, when electromagnetic radiation is incident, or we can use shone, onto its surface. All right. Once that happens, those electrons, we can say that the electrons emitted, use the right words, from the metal surface are called photoelectrons. Photoelectrons. So that's the little section, or the section that we're doing now. Please make sure the diagrams, the definitions, these little things that I'm writing down are in your books. And let's have a look at the first little topic. Subheading. Light consists of a stream of energy packets called photons. Right, your first little heading is light consists of a stream of energy packets called photons. A photon is a particle representing a quantum of light energy. Now this is important. We spoke in the previous one, I said to you that light can either be a particle or it can be a wave. Now, how we look at that, this is just a model of the representation of what I'm talking about. It's not, we can't actually see this, but let's just have a look here. In the previous one, I showed you a little diagram. So the diagram showed the light as a wave. So when I'm looking at light, light comes through as a wave, a transverse wave, and it comes through and it shines onto that piece of metal. But at the same time, within the light, the particle part is called a photon. There's a name for it. So it comes in as a transverse wave that's perpendicular to each other, but inside there's a particle part of light that is called a photon. Please get this diagram into your book so that you understand what we mean by light is a photon representing a quantum of light energy. We can even call it a packet of energy. A packet. So it has some sort of physicalness to it. It has, like we've seen in the previous, the properties, it has some sort of mass to it. Right, that's the next thing. Right. The energy of a photon so if I wanted to know what's the energy of a photon of light, I can use an equation. So the equation is E is equal to HF. All right, that's my equation. So this is for energy of a photon. This E stands for energy of a photon. The SI unit that we're going to use for energy is in joules and is a scalar quantity. The F value we use here is frequency, and that's measured in hertz, right? And the frequency, this is going to be the frequency of the light which is incident on the metal. Okay, frequency is measured in hertz, and then the H over there, the H here gives me Planck's constant, and Planck's constant H is equal to 6.63 times 10 to the power of negative 34 joule seconds. Right, this value here, because it's a constant, will be on your data sheet. So that's the one equation that we use. The second equation is they've given you in here frequency. So in terms of frequency, there are two other formulas that you can use to calculate frequency. The first formula that is relevant here is frequency is equal to 1 over t, where t is the period of a wave, which will be in seconds, and frequency over here, f is frequency measured in hertz. The second equation we're going to use is an equation we've seen before, which is v is equal to f times lambda. Now, in this kind of situation, this v over here is the velocity of the wave. But in this instance, for this section, because we're working with light waves, then we're going to use the speed of light. And the symbol for speed of light is c. And because it's a constant at 3 times 10 to the power of 8 meters per second, our formula is going to change for the speed of light, and c is equal to frequency times lambda. And that gives you your third equation there. And the only reason why you would use equation number 1 here and equation number 2 is if they don't give you the frequency, but you still need to measure the energy of a photon, there are two other options that you could use to get that frequency in order to substitute it into your into your formula so that you can do the correct calculations. All right, so that's the one thing. The next thing is, you must understand about this value C is that the speed of light of all light, that's important, or all electromagnetic waves that means radio waves, gamma rays, all of it. If it goes through air or vacuum, then the speed of light remains the same. Right? Lambda, we know, let me just go here, is the wavelength, which we've looked at a little bit. And it is measured in meters. So if they give you something in kilometers, you need to make sure that you know how to do that kind of a calculation. And I can give you this little triangle here that can just help you to manipulate your formula. C is equal to frequency times lambda, and you can manipulate it as you need to. Now these formulas help us because if I look at it like this and I say that E is equal to HF, right? That's your first one. But also F, frequency, is also equal to C over lambda. Then I can combine those two formulas, and what I'm going to get is, I'm going to get that E is equal to H multiplied by C over lambda. So this is H over 1. So now I've actually got a new formula, which is E is equal to, and that comes straight from here, HC over lambda. And that gives me a combination of the speed of light formula and the energy of photons. So I have multiple formulas. Please make sure that all of these formulas, this formula, and this formula is highlighted in your books. Just do this. So all I've got here now in this formula is that C is the speed of light, which is a constant at 3 times 10 to the power of 8 meters per second. I've got H here, which is Planck's constant, which is 6.63 times 10 to the power of negative 34 joule seconds. I've got lambda here, which is wavelength in meters. And I've got E here, which is energy of a photon, which is in joules. So you can use any one of these formulas to find either this number 1 or number 2 to find energy of a photon, but you do have this other formula here that can assist you. Right. Another thing that you must understand or you must remember is your conversions. Please remember that we have standard units, which are things like coulombs, hertz, meters, seconds, and then you have your conversions. So your conversions look something like, just give you a little table here. You should remember your engineering notation from when you were in grade 10. For example, they could give you 1 nanometer, but you need to convert that to meters. So you'll say 1 times what's nano, 10 to the power of negative 9, and that gives you your standard unit there. And that would be the unit in meters. They could give you 420 nanometers. And you'd say 420 times 10 to the power of negative 9 meters. So you'll do that kind of a conversion. If you are struggling with conversions, then you can send me a message and I'll show you how to get through this. But you need to make sure that all of your values are in meters, meters per second, joules. If they give you kilo or mega or giga or tera, You need to know this engineering table off by heart so that you're able to do the conversions. But not only that, for things like micro, for example, the symbols are quite different. So you need to make sure you know which symbol goes with the correct units. So this table, please get it down into your book so that it's just there to revive or jog your memory from your grade 10 stuff. Alright, so the two things that we're going to work with now, let's just do a little example. Alright, so the first thing over here, it says the frequency of ultraviolet light, UV light, is 2.50 times 10 to the power of 15 hertz. And then they say to you the wavelength of red light is 680 nanometers. Calculate the energy of a photon of UV and of red light. Now let's have a look at the first one. All right, for the UV light, the information that we have, or we want energy of a photon, so we have two options, but let's look at what we have. For ultraviolet light, we have the frequency, which is 2.50 times 10 to the power of 15 hertz. We know we have H, so that's sorted out. And we need energy of a photon. Now, if I look at the information I've been given, I can use the easier one, and I can go ahead and say that E is equal to HF. So that's the formula that I've chosen. The second thing I'm going to do is I'm going to substitute. I know my H value as 6.63 times 10 to the power of negative 34. And I know my frequency of UV light, and that is 2.50 times 10 to the power of 15. And you pop that into your calculator. Pause the video, engage, like I said. Pause the video, see what you get, and then see if we got the same answer. And then I would get 1.66 times 10 to the power of negative 18 joules. And there's my answer for the first one, for the energy of a photon of UV light. For the second one, red light, just have a look at the information. The information they gave you here is 680. They gave you lambda, 680 nanometers. So my first problem is that nanometers doesn't work for me. I need that to be in meters. So I'm going to say 680 times 10 to the power of negative 9. And now I've converted that to meters. So now I need to find a formula that has lambda. So if I go back to my formulas, I do have one formula. Here's it here. And it has lambda. So of the information, I've got E is equal to HC over lambda. I've got lambda. H is a constant, so I've got that. C is a constant, so I've got that. And E is what I'm looking for. So all I've got to do is substitute that in. I've got 6.63 times 10 to the power of negative 34 multiplied by C, which is 3 times 10 to the power of 8. All of that over 680 times 10 to the power of 9. And if I pop that into my calculator, I should be getting 2.93 times 10 to the power of negative 19 joules. And that's energy of a photon for UV and energy of a photon for red light. So that's the first little bit of this topic. Alright, before we go on to the next subtopic, the first thing we're going to look at is of our relationships. Right? These relationships are very, very important. The first relationship, I'm looking at both of these formulas, and what you must understand is that the energy of a photon, the energy of a photon is directly proportional to the frequency of the light. The greater the frequency of the light, the greater the energy of the photon. So when we write that mathematically, I've got that energy of a photon is directly proportional to frequency. The second thing that we look at is the energy of a photon is inversely proportional to the wavelength. So the longer the wavelength, the lower the energy of the photon. So how we write that mathematically is a little bit different. Please make sure that you write these points in your books. Right. What that means is there's no such thing mathematically as inversely proportional. There's no sign for inversely proportional. The only sign we have is directly proportional. So we're going to say that energy of a photon is directly proportional to the inverse of the wavelength. So 1 over lambda. And that is how you write it mathematically. Words, A and B are the words, and the little things that I've written on the side, those are the mathematical relationships. The next thing is, in the visible part of the electromagnetic spectrum, red light has the longest wavelength, right? And violet has the shortest wavelength. And I spoke about this at the beginning. Please rewrite it down so that you can keep engaging and engaging. Also, red light has the lowest frequency, so it's the least dangerous. But blue light or violet light has the largest frequency, and the higher the frequency, the more dangerous the type of light it is. So please make sure you write down these little points, highlight, write down your mathematical relationships, write down the relationships in words. Very, very important. They're going to ask you theory-based questions on these. Understanding that red light has the longest wavelength, it means red, yellow, maybe orange. Blue light or violet light, that's violet and indigo on that side of the spectrum, on the right-hand side of the spectrum. So please make sure that you know the difference. Alright, what we have here is the second subtopic, which is the energy of a photon is transferred to the electron in a metal atom. So if we use certain types of light, it doesn't mean that we're going to get an emission spectrum. So the first thing we should note down is that not all frequencies of light cause electrons to be ejected from the surface of a metal. So if I look at these diagrams above, if I'm using red light, for example, and I shine the red light onto a metal surface, it has a very low frequency. So you may get no electrons ejected from the metal. So I'm not going to get any electric current. What I've got here is a galvanometer. And a galvanometer is there to indicate whether there is current flowing or no current flowing. If I use low intensity light, then we're going to look at something called the threshold frequency. We'll get to that now. I'm going to get some electrons ejected, but if I use high intensity light, then I'm going to get many electrons. So make sure that this image or this diagram is in your book. So pause the video, draw it out, engage with it, so that it becomes something that you memorize and you know how to draw in an exam or test, and you know how to label it. Very, very, very important. Right, so let's have a look at what we mean by threshold frequency. If I have something called the threshold frequency, what the threshold frequency is, it's called the cutoff frequency. And the symbol that we're going to use for threshold frequency is F with a little subscript of 0 underneath it. The threshold frequency is the minimum frequency of light. of light needed, that's important, to emit electrons from a certain metal surface. So minimum frequency. So if, for example, if the frequency of the light is less than the threshold frequency, right? Just using symbols. Then no electrons will be ejected. So that's the first rule. That means that the energy of the incident photon, the incident photon means the kind of light that you shine, right, is not enough for the electron to escape. From the metal. Right? So that is if it's less than. Now, low frequency light is like, for example, red light or orange light, yellow light. You mostly use red light. So what this actually means then essentially is that you must also know that the threshold frequency is not dependent on the frequency of light, right? The threshold frequency is dependent on the type of metal. So some metals hold on to their electrons more strongly, hold onto electrons more strongly than others. So it's not just about the intensity of the light, it's also about the type of metal that we use. Right. Then if the frequency of the light is equal to or greater than the threshold frequency, electrons will be emitted from the metal surface. So what's happening now is that the energy of the incident photon, so the light that we use, is enough for the electron to escape. All right, so in addition to that, we can say that the threshold frequency corresponds to the maximum wavelength. of light. And that will result in the photoelectric emission. So that means that the longer the wavelength, so not rather the longer wavelengths of light will not result in photoelectric emission. So these little points that I've put through now, those are important theory points. So the first thing you must understand here is that if I had something like red light, the frequency is too low, I'm not going to get enough electrons ejected. If I go to indigo, for example, indigo has an intensity of light that's slightly above or equal to the threshold frequency. I'm going to get some electrons being ejected from the metal in a very small current. But if I use something like violet light and it's high intensity, and that high intensity is above the threshold frequency, I'm going to get many electrons ejected. And having many electrons ejected means I've got a very high current. All right, so these are the little points that you have to make sure that you know, so that, remember, I'm doing first all the theory behind it, so that you understand the theory of the photoelectric effect or the photoelectric emissions, and what are the different types of conditions for these photoelectric emissions. And the third subtopic here is the work function of a metal. So when we talk about a work function of a metal, the symbol here is WO, like that, right? We can say that if the frequency of the incident light is equal to the threshold frequency, and we looked at it before. We said there was going to be you're going to get electrons, but what we're talking about now is the energy. So if it's equal to, then the energy is just enough, not the most, it's just enough for the electron to be emitted from the surface of the metal. All right. So when we're talking about the work function, we are talking about the energy, not the threshold frequency. Talks about whether there will be electrons emitted or there won't be electrons emitted. The work function, when we deal with work function, we're looking at, is there enough energy? So how we put that down is we say the minimum, the minimum energy needed for an electron to be emitted from the surface of a metal is called the work function of the metal. So we have two parts, threshold frequency, will there be electrons emitted or not? Work function is the minimum amount of energy needed for an electron to be emitted from a surface. So the work function has its own formula, and the formula we have is WO is equal to HFO. So WO is the work function. And remember I said work function is the amount of energy, so we measure that in joules. H we know as Planck's constant. Which is 6.63 times 10 to the power of negative 34 joule seconds. And then FO here is the threshold frequency. And that's measured in hertz. So this is another formula that you have to, it will be on your formula sheet, but you have to know how to use the formula and what everything means so you can substitute in the right amount of information. Let's have a look at an example. Alright, the question says calculate the work function. Calculate the work function of sodium, which has a threshold frequency of 5.43 times 10 to the power of 14 hertz. So I've got my threshold frequency there. I know H, and they want work function. So we don't know that. So all we do is write down our formula. Work function is equal to Planck's constant multiplied by threshold frequency. And I've got 6.63 times 10 to the power of negative 34 multiplied by 5.43, times 10 to the power of 14. Pause your video and then have a look if you get the correct answer. Right, and the answer you should be getting is 3.60 times 10 to the power of negative 19 joules. Don't forget 2 decimal places when you're answering these types of questions, and keep your calculator in scientific notation. Let's have a look at another example. The second question here says the work function of zinc, let's get that right, the work function of zinc is 6.93 times 10 to the power of negative 19 joules. Calculate the threshold frequency of zinc. Right. So all we've got to do is see what information we do have. We have work function here. They want the threshold frequency, so that we don't have, and we know H is a constant. So same thing, formula, WO is equal to Planck's constant times threshold frequency. For this one, we've got our work function at 6.93 times 10 to the power of negative 19 is equal to 6.63 times 10 to the power of negative 34, and all of that times the work function. So divide both sides by Planck's constant, and your threshold frequency for zinc is 1.05 times 10 to the power of 15 hertz. So the calculations are pretty basic. The most difficult part is when we do these calculations, you're going to have to pull off a graph, but I'll show you how those work in the next video. So this is video number 1. Once you're done, you can move on to video number 2.